Hey everybody! In this video we're going to talk about limits and continuity, but in higher dimensions. So I'm going to refer this back to what you know from limits and then also continuity with one variable functions or single variable calculus. So starting back from Calc 1, when your functions relied on a single variable, this was your limit definition, the formal definition for a limit of a function. The limit existed in an equal this number L as long as these were true. So what this says, if you want to read it, like specifically what you read is absolute value of f of x minus L is less than epsilon whenever absolute value of x minus c is less than delta. But what that means is the difference, absolute value is difference, the difference between this y number and the limit value is small. It's less than some arbitrary number epsilon. And this happens anytime the difference between this x value and what we're approaching on the x-axis is also really small. So what this is basically saying is if you zoom in on the x-axis, then a limit exists if your function is also sort of zooming in on a y value on your, if you look at your y-axis. So that's single variable. Let's extend this definition to higher dimensions, multivariable. And so here's our new definition. So we'll say now our definition for the limit of a function of two variables is the limit. This time we're going to do x and y. So as x comma y approaches some point x naught comma y naught of our function that now depends on two variables x comma y equals L. Okay, so going from single variable to multivariable, our limit as xy approaches x naught y naught of our function that's a function of both x and y has this limit value if the absolute value or the distance between f of x comma y and L is less than epsilon. Same thing here. And this is whenever, now this is where we have to think about how to translate this part. Whenever the distance between this point and the point we're approaching is small. So how do I show that with a point in space, not just a regular x number, but with an x comma y? I use the distance formula. So that's what I was starting to write here with the square root. So the distance between the x components, so x minus x naught squared plus y minus y naught squared, and this is less than delta. So this is just extending our single variable limit definition to multiple variables. And so what this ends up looking like visually is, I'll show you actually, you're creating what's called a disk around your point in space that's your output, which is L. So let me show you what I mean. So we have our x and y axis, and this is only our input, so this is only our domain. In single variable functions, this was the input down here, and this was the output here. But now, our output, you can call it z. So it's another dimension. Like you can think of it as not even being drawn, it's coming out of the board. So all of this is just my inputs. And so visually what I can say is, let's say my x naught that I'm approaching is here, my y naught is here, and so the point that I'm approaching in space is there for as far as plugging things in, okay? And so we basically say that this limit exists if I can create this disk around that point, and the distance between our xy and what we're approaching has to be small, has to be less than delta. So where delta comes into this picture, this should be more circular, like centered around this point. My drawing's a little off. Let's make it slightly better. Okay. This delta is here. It's actually the radius of this circle. So instead of just sticking to just the x-axis and staying within the delta range on a single axis, I'm staying within a delta in terms of x and y. So that's why it's the radius of that disk. And so when this happens, so let's say our point x comma y is here. So then we'll say that that right there is x comma y. But it's close enough to what we're approaching because it's less than this finite distance away. when that's true, then our outputs, we'll graph them on a separate axis. I'll call it Z. Okay, so our outputs are really close to L. So let's say this is my L value, my f of x, y value. So if I plug in, so stick with me here. If I plug in this point into my function, x comma y, then my f of x comma y, it's really close to this limit value. It might even be that limit value. I'll just make it different to show you what I'm saying. So this right here is f of x comma y. But it's close enough to L because this part here, it's saying that the distance between this output value and my limit is really small. It's less than some arbitrarily small number, epsilon. So this right here is epsilon and epsilon. So this is like L plus epsilon, and this is L minus epsilon. And we're within that range or interval. Alright, so this is the formal side of it, just to show you the definition of our limit in higher dimensions. But the nice thing is, everything you know about limits from single variable functions, it's still going to work here. So your sum, difference, constant multiple rules, radical, power, all those limit rules that you've learned way back when you started calculus, they're still going to work here. So let's just jump right into it and work out some examples. Okay, so here's this first example. Find this limit as xy approaches 2, 8 of 3x squared y plus square root x times y. Now, if you remember when you first learned about limits, what you want to try to do is just direct substitution. If that doesn't work, then you try something else. You try some other techniques that you learned, and I'll show you a different example to use some other techniques. But let's jump right in and see if direct substitution works. So if I just plug in my values for x and y, let's see if we get a real number answer. So x is 2, so 3 times 2 squared, times y, which is 8, plus square root of x times y, so that's 2 times 8. It's looking good. There's nothing that's going to make this undefined or not real. This is positive inside the square root. So this is just 3 times 4 times 8 plus square root of 16. So this is just going to be 96 plus 4, final answer 100. So that's it. Really straightforward computation because direct substitution worked. Let's try another example where direct substitution won't work. So the limit as xy approaches 0, 0, and our function is x squared minus xy over square root x minus square root y. So if you can see it, you could just say direct substitution won't work and then move on. But let's say you don't see it and you just need to try. If we plug in 0, look what we get. 0 squared minus 0 times 0 on top. Square root of 0 minus square root of 0 on bottom. 0 over 0, which is undefined. Alright, so we have to try something different now. If you already know we needed to try something different, you could skip that step. So in this case, what we're going to end up doing, and if you kind of remember some of the techniques you learned when you first were learning about limits, one of them was to multiply by the conjugate of either the numerator or denominator. So I'm going to rewrite this function, and then you take a look and think about it. What am I going to pick and take the conjugate of it? The denominator. So the ones with the radicals usually, and it's because I'm trying to actually get rid of the problem, and the problem is if I plug in 0, 0 now, both this combination of x and y is going to make the bottom 0, which is what makes it undefined. So I'm going to multiply by the conjugate of the denominator times the top and bottom. So remember the conjugate, you just change the sign in the middle. So for us that's going to become a plus sign. And now, working on some algebra skills, so we are going to have to FOIL this out. But what I have learned with trying these problems is sometimes it's better to wait for foiling both the numerator and the denominator, and it's going to pay off on this one. So normally which one you definitely want to FOIL out or multiply is whichever one you picked to take the conjugate of. So what I'm saying is let's FOIL the denominator, but leave the numerator factored. And so for this one, I'm actually going to even factor further the numerator. And so if you notice, you can take out an x from these two terms. So my numerator is going to be x times x minus y times what we multiplied by, square root x plus square root y. And then I'm going to go ahead and FOIL out the denominator. And so we have square root of x times itself. So we got squared. So that just became x. You undid the radical. Then you get positive square root y times positive square root x. And then you have negative square root y times positive square root x. And then you have negative square root y times itself. So that radical gets squared away there. Now, anytime you multiply something times its conjugate, this is always like a nice place to check if you did your work right. The terms in the middle should add up to 0, and these do. Plus these radicals being multiplied minus the same thing. So that's how I know I'm on track. I did my multiplication correct. So now let's see what we get. So our limit as xy goes to 0, 0, and on top, I still have the same numerator. I didn't change that yet. On bottom, if I get rid of all that stuff in the middle, I just have an x minus y. And then here's where it's good to notice that we did the right thing to wait on FOILing out the top, because right here, these terms divide out. And that's good, because that was the problem. The problem was when I plug in 0, 0, the bottom was 0. So now I'm just left with the numerator. Let's go ahead and plug in 0 for x and 0 for y. So this is 0 for x times square root of 0 plus square root of 0, which the answer is 0. But the reason why this is okay and earlier it wasn't okay is because you can't ever divide by 0. And at this moment, the denominator is a nice invisible 1. This is really over 1. Okay, so the new part is just the fact that our function was a function of both x and y, but everything else is things that you've learned for limits in the past and just using some algebra techniques. Okay, let's keep going. So we actually have to consider more when we're thinking about these functions in more than one variable. And so limits of functions in 2 or more variables, there's more involved here. So for a limit to exist at a point, the limit must be the same along every path of approach. Now you know this from single variable calculus, but now that we're working with multiple variables, we have to consider multiple paths. Here's what I'm saying. In single variable calculus, we'll just sort of look at it real quick off to the side here. So single variable, you had to make sure 2 things happened. If you kind of can think back what I'm getting at. So the limit existed if something was the same. Which limits were the same? It was when you approached from the left. So I guess it's just one thing happening. These have to be equal. Approaching from the left had to be the same as what you get when you approached from the right. And that was because there was only 2 directions or paths of approach. I can approach from the left or the right of my x number because it was a single variable. It was only focusing on like the x-axis. So that's all I had to make sure of. Now I can actually approach from any direction. If you look, kind of think back on our drawing we had with the domain, the x comma y, I can draw all kinds of paths to get to that point. It's not just one left and right path. It can come in from the top, from the bottom, the side, at an angle, curve, straight, all kinds of things. And so what we have here, well, let's first say this. If we ever find paths with different limits, so if we ever find paths with different limits, then the function has no limit at the point they approach. And the function has no limit at the point they approach. Okay. Sorry, get there. Point they approach. Okay, so I'm gonna show you an image so you can kind of visually understand what I'm talking about here. And you can kind of think of it like a cliff. Okay, like if you could approach a cliff from the land that's at the top of the cliff, that's okay, but to get to the edge, that's the only way there. And then on the other bottom of the cliff, you are approaching whatever's underneath it. And so you would actually be approaching two different values. And so that limit wouldn't exist. We would say no limit exists at that point they're approaching. So let me show you so you can see what I'm talking about. Okay, so here's an example of a function where we would have like two different paths of approach and the limit not exist because of what happens. So for example, consider approaching the origin, which is right down here, 0, 0, and along different paths of this this surface. So let's say I was approaching, trying to get to 0, 0 from over here. If you kind of notice, this side of this function is going up like this toward 1. If I kind of scroll down over here, this part right here, if you can tell, approaching the origin, if I walked along here, I'd just be already on this axis and approaching 0, 0. And so different things are happening here as far as how we would end up approaching 0, 0, and that whole idea of like maybe the cliff, to where coming from one side you're approaching one value, coming from another side you're approaching another value. Alright, so we have what's called the two-path test for non-existence of a limit. And this is a test to let us know if the limit does not exist. Let me read it to you. It's really straightforward. It just says that if your function has different limits along two different paths within our domain of our function, as you're approaching the point you're looking for, so as xy approaches x naught y naught, then the limit doesn't exist. Okay, this is what we were saying. So what I want you to just kind of be aware of what this is not saying. This is not a test for does the limit exist. It's a test to prove that the limit does not exist. And also what it's not saying is if you only think about straight line paths, that's not necessarily going to imply that the limit exists. So you have to consider different types of paths, like maybe curved paths as well. So let's try an example. And so we have the following limit. The limit as xy approaches 0, 0 of 2x squared y over x to the 4th plus y squared. Okay, so what I want to know is, does this limit exist? And if I plug in 0, 0, it's going to be undefined. I can try to factor and do different things to see if what I can figure out here. This actually doesn't factor nicely at all with real numbers. So what I'm going to try is to prove that this limit doesn't exist. I'm going to see if I can find two paths. So for my test, two paths that when I approach two different ways to 0, 0, I get different values, therefore saying the limit doesn't exist. Alright, so the paths that I'm going to consider, sometimes you have to sort of think about what would be a good path to try, and I'll show you what I mean. It has to do with how the function looks, and when you pick this type of path, how it will simplify. And so here's what I'm saying. I want us to consider paths of the form y equals mx squared. Alright, so these are paths that look parabolic, right? This is an x squared equals y, so it's some kind of parabola with a coefficient that can make it like wider or more narrow. So I want to pick paths of this form, and I kind of had to analyze this to know that this was a good choice, because watch what happens when we do. So we're going to adjust here our limit. So the limit as x comma, we are now saying that our paths for y look like mx squared. So x comma mx squared approaches 0 comma. You have to actually do the work over here to think about what this is. It's still 0, but let me just show you why. So as x approached 0, what does that say here? Then plug in 0 here, m times 0 squared, y is approaching 0. So this is still approaching 0, okay? But just showing you that you have to actually kind of think about that for a second. Alright, so that's this part, changing our terms of our points. Now let's modify our function. 2x squared And where there's y's, I am replacing it with mx squared. So times mx squared, that's the numerator. On bottom, we have x to the fourth plus y, which is mx squared, quantity squared. Let's simplify, and then that way you can see where I'm going with this. So my limit, I'm just going to leave off these points for a second. My limit on top, let's see, my function becomes, this is 2 times m, x to the fourth. And then on bottom, this is going to be, let's just write it out, x to the fourth still, but this is m squared x to the fourth. M squared x to the fourth. And then we can simplify some things. Notice all the terms have an x to the fourth in it, so let's go ahead and simplify that. So we have that this limit on top 2m, because we're going to divide out that x to the fourth here, here, and here, over 1 plus m squared. And this was as x comma mx squared approaches 0, 0. Okay, so what does this say? Notice that there's no more x's left, so this actually just equals this. If we try to plug in x, 0 for x, there's no x's remaining. So this is 2m over 1 plus m squared. And so you have to sort of just say, well, what does this mean? This is my limit. This is L. This should be L. But consider two specific paths. Right now I kind of generalized it. Any parabolic path like this. So what if I say I want the path when m is 1? So when y equals 1 times x squared. Okay, so then my limit here, L, let's just write that there, L would be 2 times 1 over 1 plus 1 squared. Okay, so that's 2 over 2, so that's 1. Alright, well let's say I choose m to be a different number. Let's say, let's just go right here. Let's say m is -1 or 2 or anything else. So I'm going to go with 2. So then y is 2x squared. So then my limit value, what I'm thinking is my limit, is 2 times 2 over 1 plus 2 squared. So that's 4 over 5. And they're different. Okay? And let's say you pick two numbers for m and you got the same value. You might want to just try a third one and see if you get a different value, to see if you can just find two paths where the limits don't meet the same thing, don't equal the same thing, so then this limit doesn't exist. Because these are not the same, this limit doesn't exist. We just took two different paths, tried to approach 0, 0, and got different values, so therefore doesn't exist. Think about it in single variables. If you came in from the left and the right, you're getting two different values as you approach this same singular point. So you could say, by the two-path test, this limit doesn't exist. So let's just put that there to be formal. So this limit as x, y approaches 0, 0 of our original function, which I think was 2x squared y over x to the fourth plus y to the second, does not exist by the two-path test. Okay, let's try another one. So we're going to show that this limit doesn't exist as we approach the point 0, 1, where our function is x times the natural log of y divided by x squared plus natural log of y quantity squared. So let's think about some paths and we'll try them and see what happens. So when we pick a path, we still have to end up approaching the same point that we're supposed to approach, which is 0, 1. So I'm going to let, so for path 1, I'm going to let y equal 1. I'm going to pick a straight line path where it's line y equals 1. And if you think about it, that still approaches the same point because x approaches 0, and then if y is 1, it's definitely approaching 1. So if I go right into my limit here, this is now the limit as x goes to 0, since y is 1. And then x times natural log of 1 over x squared plus natural log of 1 quantity squared. Okay, Now simplify. Natural log of 1, if you remember, that's just 0. Because natural log is saying e to what power equals this number. So e to what power is 1? The answer is 0. So this is the limit, let's go down here actually, the limit as x approaches 0 of x times 0 over x squared plus 0 squared. Now, if I simplify this, my numerator is 0, so I have my limit as x goes to 0, over my denominator, which is x squared. And now, be careful, don't take your limit just yet, because if I plug in 0 for x, it's going to be undefined. But, if you think about it, without approaching anything, I still actually have to simplify. So I'm still on the simplified step. 0 over anything other than 0. So, as a function, so if I kind of take off limit from all of these steps, if you just sort of think about simplifying our function. So if I ignore all this, 0 over x squared is just a constant 0. So this is really the limit of 0, which is 0. Okay. So approaching along the path y equals 1, our limit value is 0. Let's try a different path and see what we get. So path 2, and let's see what's a good path if I sort of think about the fact that I'm using natural logs. Maybe I should introduce e to some power. And so what I'm going to do here is I'm going to let my second path be e to the x. Now we have to just make sure that we're still going to approach the same point. So we'll say, notice, as x approaches 0, then y equals e to the 0 approaches 1. Okay, so we are still in fact approaching the same value. X goes to 0, and if we plug in 0 here, y is going to 1, which is good. Okay, so let's use that as our path number 2. So from here, plugging that in for y, so the limit as x goes to 0, and then y goes to e to the x, we are going to, actually I guess I should put that there. So x and then e to the x, 0 comma 1, approaches the same point. We have x times natural log of e to the x over x squared plus natural log of e to the x, quantity squared. Alright, now let's simplify. Natural log of e to a power is the power, because remember what this is asking again. Natural log is saying e to what power does this equal? Well, natural log of e to the power, the answer is right there. It's x, it's the power. So this is our limit as x, just focus on x goes to 0. On top, this is going to be x times x, because what I've been saying, this whole thing here is just x. If you go back and think about your rules of logarithms, I'll show you if you're confused on that. This is log base e, and this is of e to the x. So it's asking you e to what power is e to the x. So the answer is that power. And so this is also just x. So this is on bottom, x squared plus x squared. So let's move back up here. And we have the limit as x goes to 0. On top, x squared. On bottom, 2 quantity x squared. Okay. And if we simplify, this is the limit as x goes to 0 of 1 over 2, because the x squareds divide out. And now we consider plugging in 0, but there's no more x's, so this is 1/2. So, by the 2-path test, we got 2 different limits, so you can say, therefore, this limit does not exist. Okay. And so, like I mentioned before, real quick, just because 2 straight line paths, or even all straight line paths, have the same limit, you have to consider curved paths as well. So we did one straight line path, but 1 curved path. So the fact that they didn't equal the same thing was good. Alright, so next we're going to talk about continuity. So for continuity, this idea here is exactly the same as what you know from single variable calculus. These three things have to be true. So, number one, your function is defined at the point you're approaching. Number two, the limit of that function exists as you approach that point. And number three, think about it, what either you remember or what you could just sort of reason through right now. The function is defined at the point. The limit exists as you get close to that point. Number three is that the limit is the number you get when you plug in this point, or this f value. This part one. When part two and part one match up is part three. So when the limit of your function equals the actual function value, then the function is continuous at this point. Okay. So when we're talking about continuity of a function, we're kind of interested in where it might be discontinuous. And so you try to exclude those things, and then you say, okay, on this domain, then the function's continuous. So let's try out an example. All right, so at which points is the function continuous? I have two different functions for us to look at here. And you kind of want to just think about what would cause a problem. And the problems are fairly consistent. It's either like dividing by 0, because it's undefined, or square roots of negatives, because that's imaginary, things like that. So function a here, f of xy, is e to the xy power. Okay, so e, the natural exponential function, e to some power, that's defined on all real numbers. So e to some power, if you want to just sort of break this into two parts, e to the u, the domain, is defined everywhere. So it's everywhere, all real numbers. You can plug in anything into that function. Now, this power, this exponent, if we break that down, x over y, this has a problem. We cannot divide by 0, so this would be undefined if y was 0. So we want to make sure y is not 0. So if I kind of put these two things together, the only real issue is y can't be 0. So this function is continuous everywhere y is not 0. So notice you're plugging in for both x and y, so you can say continuous on this set. So you could say the squiggly braces for the set of all x's and y's. So all x comma y values, and then as long as, or this line actually means such that y is not 0. And you can say this a few different ways, but that's essentially the same thing here. It's continuous everywhere as long as you don't pick y to be 0. That's the only problem. So this next one here, notice it's actually a function of 3 variables. So just for reference, if this has 3 inputs, your output has to be something else. So just so you're aware, on this one the output would be another letter, maybe like w. So f of x, y, z equals 1 over z minus square root x squared plus y squared. So the big picture here is that you have 1 over something. So this would be problematic if the denominator is 0. So on this one, we have to make sure the bottom is not 0. And then within the denominator, we have a radical. So with any radical, we have that the radicand has to be 0 or more. So we'll say the radicand has to be greater than or equal to 0. So we have to sort of put these together. So on this one, that means x squared plus y squared has to be 0 or more. Well, there's nothing really to do here, because right here on this one, this is always true. So that's nice. That one's always true, because if you square anything negative or positive, it's going to turn positive. And then when you plug in 0, you just get that this equals 0. So that part's taken care of. So going back here, the denominator can't be 0. So if we focus just on that part, the denominator, we have z minus square root x squared plus y squared cannot be 0. So this is what we have to exclude. Let's just make it look a tiny bit nicer. Z equals square root x squared plus y squared. And then if I square both sides, z squared equals x squared plus y squared. But this was the problem. We don't want this to happen, so we cross this out. So this function is continuous, so we can say continuous, everywhere z squared is not equal to x squared plus y squared. Okay, so that's it for this one. Your limit rules still apply from Calc 1 here. It's just multiple variables in your inputs. And then continuity, kind of just look for the problems and then exclude those from what you get to plug into your function. Exclude them from your domain. And then your two-path test to show if a limit does not exist. All right, take care, everyone.